Okay, so this is Lecture 2, Part 8, the final section from Chapter 2. Lecture 2, Part 8. And in this lecture, we're going to talk more about properties of derivatives of functions. So I'll start out with an illustration of how we interpret information from a derivative. So consider this picture. All right, so the blue curve is the graph of f of x. So here we have f of x drawn in blue. And notice I have not given a definition for f of x. That's an arbitrary function that's continuous on this particular interval along the x-axis. It's a smooth curve. It has no gaps or holes or sharp corners. And what we want to do is we want to calculate the derivative of this blue curve at all values of x, where f of x is shown. All right, so now the red curve in this illustration demonstrates f prime of x. All right, so before I discuss how the red curve was derived, I can give you the definition of the derivative of a function. So recall, the derivative of a function at x equals a is the limit of the difference quotient. That's one definition. So I'll write it here for your reference. Okay, so there's the derivative of a function. And now, we want to find this derivative for all values of x along the x-axis where f of x is shown. So clearly, a is each number along this x-axis. So why not simply replace a with x? Right? And then if we do that, we'll have a generalized expression for the derivative of a function. So I'm going to replace a with x because a, in this case, can be construed as the parameter or the variable. So the generalized equation for the derivative of a function is this. For any x, as long as x is in the domain of f. So all I'm doing is simply replacing a with x. And then, all right, so, okay. So now, let's discuss how we calculated the red curve from the blue curve. Now the red curve is, as shown here, f prime of x. All right, well first of all, recall what the distinctive definition of the derivative is. The derivative is the slope of a tangent line to a graph at the point of tangency, right? So if you pick any point along the blue curve and then calculate the slope of the tangent line, as we've done in the prior sections, you'll get a number for each x, okay? And that's shown in this equation right here for f prime of x. So choose an x and then calculate f prime of x. Okay, and that becomes a number because remember, why is it a number? Because remember, a limit, if it exists, equals to L. All right, so that's what the derivative is doing. So at each x along the x-axis, we calculate the derivative of the function, which happens to be a limit, and the limit, if it exists, is a number, L. So in this case, look where I've drawn this tangential line in black. Clearly, let me say there's the point of tangency right there at x equals 0. So clearly the slope of the tangent line to f at x equals 0, that's a negative slope. We can deduce that just from our knowledge from algebra. Any line which has this configuration, which is shaped like this, any straight line will have a negative slope. So that means that if we were to plot, basically what's going on with the red graph is we are plotting a function table x and L. Okay? So the x's on this x-axis correspond to the x's on the x-axis for f of x. So for a particular value of x, we get an L. And so in this case, at x equals 0, L is a negative number, and that's shown right here. So at x equals 0, L is negative. So note, here's our L at x equals 0. Now L is the limiting value. Okay? And so we continue to see that we have a sequence of negative slopes up to a certain point, right? So look at all these slopes. Look at what happened. Okay. Look at the progression of tangential lines, the sequence of tangential lines. So at each x, I compute the slope of the tangent line at each x, and up until I get to this point A, okay, all of the slopes of the tangent lines are negative. And so all of my L values are less than 0 for x less than A. So there's my function table. If x is less than A, then L is less than 0. And that's depicted on this graph. Okay, this A right here for f, okay, corresponds to the A prime for f prime of x, right? And so as long as my, okay, so here's some, we'll call this x naught, okay, and then we'll call this x0 or x naught. As long as x is less than x naught, then my L values, as shown in this function table, are less than 0. And so the outputs of this function f prime of x will have negative values, and that's shown, demonstrated in this curve. The function is below the x-axis for x less than x naught, okay, which corresponds to A prime. I hope you see that. Okay, now when I get to point A, notice that point A is a transition point where the slopes transition from, that is the slopes of the tangent lines, transition from negative slopes to positive slopes. Okay, see how the slopes transition from negative to positive at point A? But in this transition, to go from negative to positive, we have to step on 0. Okay, and when we step on 0 as the slope of the tangent line, we have, as we've discussed before, note that A is a local minimum point for this function because the slope of the tangent line is 0 at this local minimum point. And it's also a local minimum point because to the left of the minimum, the function is a decreasing function, and to the right of A, the function is an increasing function. And so we have another basically concept for what the definition of a decreasing function is. A decreasing function has the property that the slopes of its tangent lines are less than 0 on the interval of decreasing. Okay? On the interval of increasing, the slopes of the tangent lines, as shown in red, are positive. All right, so if the slope of the tangent line is 0 at A, okay, so at x equals A, the slope is 0, well, we plot x naught 0 on the graph y equals f prime of x, and that's shown right here. Okay? Even though f of x 0, f of x naught is 1, okay, f prime of x naught is 0, okay? They have two distinct outputs. All right. Okay, so the same concept holds for point B. So before we get to point B, however, notice that the slopes of the tangent lines are positive. Okay, so between A and B, the limit, this limit is a positive number. So for x, okay, so let me clarify. This is a function table for f prime of x. I guess I better clarify that. Okay, so if x is between a and b, L will be greater than 0. Although we don't know what it is, it's going to be greater than 0. And so that is shown on this graph, f prime of x. Okay, between a and b, a prime and b prime, L is greater than 0. So that means that the graph has to be above the x-axis between a and b. And that's shown here because the slopes of the tangent lines to the function are positive, right? And the L values, which are essentially the slopes of the tangent lines, are all positive. Now at B is another transitory point. Okay, at B, the slopes of the tangent lines to f of x transition from positive values to negative values. You can see that here. These slopes, drawn in blue, have negative slopes. And to transition from positive slopes to negative slopes, you have to step on 0. And that's why the slope at B is 0. And that's depicted on this graph for f prime of x. At B, at x equals B, we'll call it, say, x1, for instance. All right, so at x1, x sub 1, they call it b prime. Okay, the slope of the tangent line is 0, and that's shown for the graph of f prime of x. Now, again, as we transition from an increasing function to a decreasing function, we have the point of transition will produce or force a local maximum. So you can see that b is a local maximum because we're going up and then we start going down. And when you do that on a curve, you have to go through a peak value, okay, a local maximum. That's just intuitive and geometric concepts. Okay. All right, so between B and C now, between B and C, we're going downhill. Okay, the slopes of the tangent lines are all negative until we get to C. Okay, and so at C, we'll just call this x sub 2. So between x sub 1 and x sub 2, okay, or in other words, when x is between, well, I guess I should say at x equals b, right? So at x equals b, L is 0. All right, and then between B and C, when x is between B and C, L is less than 0. And that's why it's shown on the graph. This is the only geometric structure that can connect B and C and still be below the graph. Note that I don't have any sharp angles or discontinuities because, as we'll show later, the derivative of a continuous function is a continuous function. And continuous functions don't always have sharp corners, but for sure they don't have gaps or holes. Okay, so we're continuous on B to C, and it should be a polynomial that's smooth and no sharp corners. And we'll talk more about that theory forthright. Okay, all right, so now from C to P. Okay, so what's going on from C to P? How would you characterize f of x? Well, again, from C to P, and we'll stop at P, the slopes of those tangent lines are positive. So at x equals C, L is equal to 0. All right, and then from C to P, so if x is between C and P, the L values, the limit values of the difference quotient will be greater than 0, and that's shown right here on the graph. Okay. All right, now at P, they actually hardwire some numbers. Okay, so it looks to me like, what are the coordinates of P? Well, they actually gave you a slope. Evidently, this yellow line right here, or now I've shaded it to green. You see this tangent line at P. Evidently, they will take M to be the slope of the tangent line at P, and so that would be, say, 3/2. So if we consider the slope at P, the slope of the tangent line to F at P is 3/2, then we have the coordinate for a point on f prime of x. Okay, so that would be 5, x equals 5, and then 1.5 is the slope of the tangent line to f of x at x equals 5, and that's 1.5. So that's the explanation. That's how you basically construct derivatives and the graphs of derivatives. So I guess we could do an example. Let's calculate the derivative of a function. How about x cubed minus x? So let's say f of x is equal to x cubed minus x, and I want to calculate the derivative of this function. All right, so what is f prime of x? And so that's the limit as h approaches 0 of the difference quotient. So that would be f of x plus h minus f of x divided by h. All right, and now make the substitutions for f. Compose f with x plus h. Okay, and so this would be x plus h quantity cubed minus, minus x plus h. Okay, so that would be f of x plus h, then minus x cubed minus x. Okay, so I'm basically wiring up the difference quotient for the function, and all of that divided by h. All right, and so that's equal to, so I'll have to complete the cube on the binomial, and I'll probably use something like Pascal's triangle. Now on the class website, there is a binomial calculator, so you can calculate the powers of binomials. I do have an expectation that you can complete this cube using some other facility without having to use technology assist. Okay, and that's basically from algebra. You can use Pascal's triangle. You can multiply it out. And you can number of resources available that you can refresh yourselves on how to expand the polynomials, or especially the cubes of binomials. All right, so x plus h cubed would be x cubed plus 3 x squared h plus 3x h squared plus h cubed minus x minus h minus x cubed plus x. So that would be the numerator, all of this divided by h. And so we can probably do some cancellations in the numerator. Let's see what those are. So cancellations would result in what? The x is canceling, the x cubes canceling. What else can cancel? That's about it, right? Okay. And then after the cancellations, we can divide by h. So this would be 3x squared plus 3x h plus h squared minus 1. Okay, so I just did the division, and now we have a polynomial in h, so we can use the direct substitution rule, and we're left with 3x squared minus 1. Okay, so that is the derivative. So this cubic function, the derivative of this cubic function is a parabola, and I believe I have a drawing. Let me pull one up for you. Bear with me. And I think this may be in your text. Okay, yeah, so here we go. So the blue graph is, this is x cubed minus x. And the red graph is 3x squared minus 1. Okay, and you can see that this portion of the graph conforms to the part of the graph that's above the x-axis for x less than, say, right here. So the green portion of f corresponds to the green portion of f prime of x. And let's see, let me change colors, change to purple. So this purple portion of f, okay, corresponds to the purple portion for f prime of x, this part right here. And then, say, the blue portion, the blue accentuated portion of f, corresponds to the blue portion for f prime of x. Okay, and that was just like the example I started off with the class. So try to understand how these are managed, how these colors conform to each other. Okay, so how about we take the derivative of the square root function? Do that next, right? So we'll just work a number of problems. So f of x is equal to the square root of x, and we want to calculate f prime of x. That's a useful function. All right, so again, use the definition of the derivative. So this would be the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, and so we'll substitute in the definition of f into the difference quotient. So that would be the square root of x plus h minus the square root of x over h, and we'll simplify this. So I'll multiply upstairs and downstairs by the conjugate of the numerator. So that would be times what? The square root of x plus h, this is the conjugate now, plus the square root of x divided by the square root of x plus h plus the square root of x. All right, and now we'll simplify this limit. So that would be x plus h. So we have x plus h minus x divided by h times the square root of x, sorry, mistake there, times h times the square root of x plus h plus the square root of x. Okay, and so that is equal to the limit as h approaches 0 of h over h times the square root of x plus h plus the square root of x. And now we can cancel the h's. Okay, so the h's go away. That becomes a 1, and we can use direct substitution because h equals 0 is in the domain, and so after direct substitution, this would be 1 divided by h equals 0, so 2 on the square root of x. Let me check that. Make sure that, yeah, 1 divided by 2 on the square root of x. So that's the derivative of the square root function. And I believe I can show you a picture of this. So let me grab it from the text. Okay, and so let's analyze these graphs. So the blue curve is the square root function, and then the red curve is the graph of, right here, 1 over 2 times the square root of x. And you can tell that the square root function is an increasing function on its domain. Okay, so as x grows larger, the slope of the tangent lines remain positive, and that's shown here. You see in the derivative, as x grows larger, then the L values are all positive, and that's shown here. Okay, although the L values get smaller and smaller as x grows larger, they're always positive numbers. Now, what happens at x equals 0? What is the slope of the tangent line at x equals 0? Well, it's almost vertical. Okay, and we know that the slopes of vertical lines are infinity, and that's shown here by the asymptotic nature of the graph. It's asymptotic with the positive x-axis. So it all fits together. All right, so let me do one more example. Let's find the derivative of a rational function. So f of x is equal to 1 minus x over 2 plus x. All right, and so we'll use the definition. The derivative of the function is the limit of the difference quotient. Okay, and now we'll substitute in our function. So this would be the limit as h approaches 0 of 1 minus x plus h divided by 2 plus x plus h minus the function 1 minus x over 2 plus x all over h. And so we have to calculate this limit. All right, so what is that? So this is equal to the limit. So I'll go ahead and do the subtraction in the numerator. The limit as h approaches 0 of 1 minus x minus h times 2 plus x. Okay, minus 1 minus x times 2 plus x plus h. Okay, all of that divided by h times the common denominator, which is 2 plus x plus h times 2 plus x. So all I'm doing now is 105 and 107, math 105 and 107 tasks. All right, so I'll do the multiplications in the numerator. Okay, and so that would be 2 minus x minus 2h minus x squared minus xh minus 2 minus x plus h minus x squared minus xh okay, all of that divided by h times 2 plus x plus h times 2 plus x, okay? And then we'll simplify the numerator. So that would be the limit as h approaches 0 of, well, let's see where we have a bunch of cancellations going on here. 2's cancel, minus x's cancel, the minus x squares cancel, and the minus xh's cancel. A lot of nice cancellations here. And so we're left with minus 2h plus h. Is that right? No, I'm sorry, minus 2h minus h. So that would be minus 3h divided by h times 2 plus x plus h times 2 plus x. And now the h's cancel. And we can use direct substitution for this remaining or resulting rational function because 0 is now in the domain of the resulting rational function. And so we're left with 3, negative 3, divided by 2 plus x squared. So, okay, so that would be the derivative. Now, on the class website, I do have a derivative calculator, and what you can do is you can take f of x and you can plug it into the derivative calculator, and you should get this result. Okay, so give it a try if you can find it. All right, so some nomenclature for derivatives. Now there's a lot of symbology for derivatives. So f prime of x in the literature, you'll see this in the text, can also be written as y prime of x. And in chapter 3, we're going to write this, dy over dx, which stands for differentials. And we'll talk about this. This is a geometric representation of the derivative. You can also write it as this. So there are a lot of different ways of writing the derivative of a function. Okay, or you can write it like this, where the derivative is an operator, kind of like the limit operator. You can do this, or, not to be confused with the domain, if this were a domain symbol, we would use parentheses, but without the parentheses, it becomes the derivative. Or, for all you engineering majors, you'll see it written like this. Okay, and if you go on to take Calculus 3, this is probably the symbol right here that you'll use. The derivative with respect to x of f of x. So all of these are symbols for the same quantity. All right, so I want to give you a definition now. We'll paste it in from the book. Okay, so a definition. So a function is differentiable at a number a if f prime of a exists. All right? It is differentiable on an open interval a to b, or a to infinity, or negative infinity to a, or negative infinity to infinity, if it is differentiable at every number in the interval. Okay? So this is what we mean by differentiability. If the derivative exists at all the numbers on the interval that you're considering for differentiability. Okay? So if you have a an interval where a function is not differentiable, then it's not differentiable on that subinterval, but it may be differentiable on another subinterval, as we'll show next. We're going to calculate the derivative of the absolute value function. Okay, so let's try and do that. So that's the question. Does f of x equal, which equals to the absolute value function, what is the derivative of this function? Now we know what the graph looks like. So this is the graph of the absolute value function. And it looks, now f of x is a continuous, f of x, which is equal to the absolute value of x, is a continuous function. So it is a continuous function. Okay, it exists for all values in its domain, which is the entire x-axis. So it is a continuous function. So let's calculate its derivative. All right, so before we do that, okay, to calculate, remember the notion that whenever you do any kind of mathematical operations involving absolute value, the strategy is to reformulate the problem into one without absolute value. So you replace the absolute value with its definition. So in this case, the way we'll handle calculating the derivative, so we want this. So if we'll start off simply by saying if x is greater than 0, then absolute value of x is just equal to x by definition. Okay, so let's process this by, well, the way I'm going to deal with this is we're going to use the difference quotient. So we know that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So we'll, now in this case x is greater than 0, so we're going to confine our derivative calculations to this ray on the x-axis, the positive x-axis right there shown in red. Okay, so when I plug it in, the function, the definition of f, I'll have the absolute value of x plus h minus the absolute value of x divided by h, and that's the limit. Okay, so I forgot to put the limit, sorry, I forgot to put the limit. So that would be the limit as h approaches 0 of the absolute value of x plus h minus the absolute value of x divided by h. Okay, now what is this limit? All right, so x is greater than 0. So we're talking about values of x on this red trace here, on this red ray. And so x plus h, basically, if h is approaching 0, we assume that h is also, we presume that h is also on this red ray as well. So we're going to assume that, we'll assume in calculating this limit, assume that x plus h is also greater than 0. And I think that's a pretty safe assumption because in the end, h is really going to be very, very close to 0, almost negligible. Okay, so if we make this assumption, then our limit, I mean, it would be absurd to think that x plus h would be less than 0. That would mean that your h would be out here, and you'd have some very, very large h far away from 0. So you're essentially going in the wrong direction. So the assumption based on geometry is that x plus h would be greater than 0 because, and then we'll go towards 0 in this direction. Okay. So we can cast off then the absolute value because x plus h is greater than 0, x is greater than 0, and so our limit becomes the limit as h approaches 0 of x plus h minus x over h, and that's just equal to 1 after you simplify it. And it makes sense because what is the slope of this line segment right here, or this ray right here? Okay, well this ray, you know, is equal to y equals x. And if you choose any point, then the slope of the tangent line is essentially the line itself, the slope of the line itself, and that's just equal to 1. So intuitively it makes sense. So for x greater than 0, we have the derivative of the absolute value function equaling to 1, right? Now we'll choose, say, we'll go in the other direction, x less than 0. So let's calculate the slope of the absolute value. Let's calculate the slopes of the tangent lines to the absolute value function along this ray, which I've outlined in green. So the second part of this exercise would be if x less than 0, then the absolute value of x is equal to negative x. Okay, and so f prime of x would equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And so I'll plug in the definition for f, and so that would be the limit as h approaches 0 of the absolute value of x plus h minus the absolute value of x divided by h. Now, okay, so since h is approaching 0, h is approaching 0 from the left. And so that would mean that h would have to be less than 0. And so if h is less than 0 and x is less than 0, then x plus h would be less than 0. And by definition, the absolute value of a negative number is the negative of the number. Okay, because we're approaching 0 from the left. All right, so if, for emphasis, I guess you could say this right there. Okay, we're almost doing a left limit. Okay, we're taking the left limit, although technically speaking we're not. You can kind of, that's intuitively what's going on. All right, so x plus h being less than 0, so this would just be the negative of x plus h. And the reason why I want to say this is because we have to, in order to take this limit, we have to do it without the absolute value. We have to undress the absolute value. Okay, so this would be negative x minus h, and then minus x. Because again, x is less than 0, and so the absolute value of a negative number is the negative of the number. And so this, after simplifying, becomes negative 1. All right. Okay, so now, yeah, so that's so far so good. So it appears that the derivative of the absolute value function is piecewise defined for all values of x, where x is not 0. So we've accounted for almost all the entire x-axis. Now we have to evaluate the limit, or the derivative of the absolute value function at x equals 0. Okay, so what is f prime of 0? Okay, so again, we use the fundamental, we use the difference quotient. So that would be the limit as h approaches 0 of the absolute value. So instead of x, we'll go back to using a again, right? So that would be 0 plus h minus the absolute value of 0 divided by h. Okay, and so so we can, in order to evaluate this limit, we can we'll have to do it based on left and right limits. Okay, we can't do it directly. So if h were positive, okay, so h would approach 0 from values of 0 greater than 0, and so the absolute value of a positive h is just h, and so we're left with h over h, and so that's equal to 1. All right, now how about, so remember we're evaluating this limit, okay, for negative h. So if h were approaching 0 from numbers less than 0, okay, well, the absolute value of h then becomes a negative h, because h is negative, right? If h is approaching 0 from the left, h has to take on negative numbers. And so that would be negative h over h, which is equal to negative 1. Aha. So look at this result, okay? The derivative of the absolute value function at 0, the limiting values are in conflict, okay? So what does that mean? That means that f prime of 0 does not exist. Because when we use the definition of the derivative, the left and right hand limits produce different results, and therefore it doesn't exist. So let's see here. So do we have a problem here? Well, no, we don't have a problem. We just have to be careful when we deal with the derivative of the absolute value function. We just can't differentiate the absolute value function at 0. It's not differentiable at x equals 0. So let me show you the pictures of the absolute value function and its proposed derivative. So we have something that looks like this. Okay, so the blue curve is the absolute value function, the graph, and the red curve is the derivative of the absolute value. So as we've shown, f prime of x is 1 for x greater than 0, f prime of x is negative 1 for x less than 0, and at 0, it doesn't exist. Okay, so the red curve is the derivative of the absolute value function, the graph of it. And it makes sense. It makes sense. So we have negative slopes, tangential slopes to the left of 0, which is shown in the red ray, and we have positive tangential slopes for x greater than 0, and at 0, we don't have a tangent. There is no tangent at x equals 0. And this is typical of graphs with sharp corners. So at x equals 0, notice that the absolute value function has a sharp corner. And functions that exhibit this behavior with sharp corners do not have derivatives at those sharp corners. We cannot differentiate around a sharp corner. A very important fact about functions and calculus in general. Okay. All right, so now I want to give you a very, very important theorem. So I'll paste it in here from the text. Stand by. All right, so we have this. If a function is differentiable at a number, then the function is continuous at the number. Okay. This is not true. The converse is not true because, as we just showed with the absolute value function, the absolute value function is continuous at 0, but it's not differentiable at 0. So this is a one-way theorem. If it's differentiable at a number, it's continuous at a number. Okay, and here's the proof. The proof isn't, technically speaking, the proof has some errors in it. I won't go over it in too much detail, but this is what's exhibited in your book. So I won't require you to to be able to reconstitute this proof, but here it is. You can read it, try to understand the algebraic manipulations that are going on in the proof. There may be a WebAssign problem similar to this, but otherwise we'll go with this theorem and leave as is. Okay, so the next topic is where functions fail to be differentiable. So let's kind of build a facility for where functions fail to be differentiable. And I'll show you some illustrations of some functions which exhibit non-differentiability at certain values, certain intervals. So let me paste an illustration into whiteboard. Okay, so if functions have vertical tangents, okay, so and we'll discuss this about what later on in the class we'll graph some functions with vertical tangents. But a vertical tangent is a function that exhibits this property. Although it is continuous, but the limit of, as x approaches a, of the derivative is infinity. Now this is not the absolute value, okay? F prime of, if for instance in the absolute value function, if this were absolute value and a were 0, well, it's not, this limit would not be infinity, it would be it does not exist. So if you encounter a situation where the limit as x approaches a, right here, where of the derivative were infinity, that is, if the derivative produced an infinite result in a limiting process, you would have a vertical tangent. That's how you identify them. So in this case, we don't consider the function to be differentiable at x equals a. So if non-differentiability would either constitute a sharp corner like this, okay, or a vertical tangent, which would look something like this. Okay, so there's a distinction between the two, and of course at a discontinuity, right? Because that slope doesn't equal to that slope in the limiting values, right? So when you have discontinuities, vertical tangents, or corner points, we do not have differentiability. All right, and then the final topic would be higher derivatives. Okay, so you may have surmised by now that derivatives of functions are essentially functions. And if you can take the derivative of a function, why not take the derivative of a derivative? And in fact, you can. So what we mean, say, if we wanted to calculate the second derivative of a function, we can do this. We can take the derivative with respect to x of the derivative of a function. Okay, and this would be the second derivative. And you could write it using superscript notation. This would be written as d squared y over dx squared, although these aren't squared operators. This is the notation for the second derivative. Okay, and so you can also write this as f red double prime, 2 tick marks. Okay, and it's the slope. It's the slope of y equals f prime of x at the point x f prime of x. So derivatives have tangent lines, and the tangent lines have slopes, of course. So how about we calculate the second derivative of this function? So if we say f of x is equal to x cubed minus x. So from a previous exercise, I believe we showed that the derivative of this function was 3x squared minus 1. So let's calculate the second derivative. And so again, we have to use the definition of the derivative because the second derivative is the derivative of the derivative. So we do this. And so this would be the limit as h approaches 0 of 3 times x plus h squared minus 1 minus f of x, which is 3x squared minus 1, all divided by h. And now we'll simplify that. So that would be the limit as h approaches 0 of 3 times x squared plus 2xh plus h squared minus 1 minus 3x squared plus 1 all over h. So that's equal to the limit as h approaches 0 of 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 over h. Okay, and so we have some cancellations, I believe. The ones will cancel. And then we can do the division. Oh, and the 3x squares, of course, will cancel. And so we're left with the limit as h approaches 0 of, I'll do the division, 6x plus 3h, and so that's a polynomial in h, and so that's just equal to 6x. And I believe I have a picture I can show you. So showing the function, its first derivative and its second derivative. Oops, wrong picture. Is it? Oh, I need to get it from here. Sorry, bear with me. Yeah, here's the picture. So let me paste the picture. All right, so the red curve is f, 3x squared minus x. No, I'm sorry. F, sorry, let me write it again. F is x, what did we say f was? F is x cubed minus x. Okay, and that's shown in red. And then we said f prime of x is equal to 3x squared minus 1, and that's shown in blue. And then the second derivative is equal to 6x. Okay, and that's shown in yellow. Now, a potential test question. It would be reasonable as a question, homework question and or test question, if I sketch the graph of the blue, red, and yellow graphs, okay, like this, if I gave you this illustration, and I would ask you to pick out f, f prime, and f double prime, using your knowledge of the geometric properties of the derivative. So if I gave you these three graphs, I would ask you to identify what is f prime, and what is f double prime. So see if you can do that based on knowing that the derivatives are slopes of tangent lines. Okay, and you also need to have knowledge of where a function is increasing and decreasing. So if a function is increasing, then the slopes of its tangent lines are positive. If a function is decreasing, then the slopes of its tangent lines are negative. At a local minimum point, the function transitions from a decreasing to an increasing function, and the slope of the tangent line at a minimum is 0, and the slope of a tangent line at a maximum is 0, and at a maximum point a function transitions from an increasing function to a decreasing function. So you have to know all of that to be able to identify which graph is f, which is f prime, and which is f double prime. What else? Okay, check the notes here. Is there anything else? Oh, okay. And then, of course, we can take a physics perspective. We know that velocity of a projectile is the change of the position with respect to time, the derivative of the position function with respect to time, and now we have acceleration. So acceleration of a projectile is the change in velocity with respect to time. So that's a rate of change. Okay. All right. So this concludes the lecture for Chapter 2. Now, I expect you to have, in very short order, all of the WebAssign for Chapter 2 completed, as well as the project. And so you'll be turning in your project, your paper-based solution to project, in one of our class meetings, unless I tell otherwise. And we should be anticipating having a Chapter 2 test soon. So consult the schedule on the class website to see what date that will be. And of course, always contact me for any hints to solutions to homework problems or to project problems. I have an expectation that as you work through the problems, that you don't spend too much time answering a problem. These problems were designed to be solved in 10 minutes or less. So if it's taking you longer than 10 minutes to solve any problem in the homework set or on the project, you need to contact me and request a hint. So I'm looking forward to seeing how you deal with that. All right, so that's the end of Chapter 2.